Good afternoon, everyone. How's the session go so far? Amazing, amazing. Love the energy here. I feel like it's been such a long day, but we're almost there. So stick with us. Today, we're going to talk about building global ecosystem for physical AI. My name is Wang. For the past 11 years, I've been working as a Silicon Valley venture capitalist, investing everything in the frontier technology sector. So currently, I manage a few funds. One is with Outpost Capital. The other is more on the AI infrastructure side called Solaris Venture Partners. Recently, me and my dear friend and partner Michael, we started a new journey together called DevMath Ventures. It's a combination of a research lab plus a venture fund. So today we're gonna talk about building global ecosystem for physical AI, and also we're gonna talk a little bit about how at DevMath Ventures, how we are approaching this particular problem. You see, AI is entering into the physical world. But when the AI is entering the physical world, it's not as easy as what's happening on the screen. Actually, nowadays, large language model is doing pretty good, right? We feel like the software side of the intelligence is almost a solved issue by now. But on the hardware layer, the hard part is not only intelligence. Intelligence is only one layer of the challenges in the entire physical AI stack, right? So, if we think about it, physical AI is a little bit too complex for one company, for one country, or for a simple technology stack. It takes multiple layers, and there are many ways on how we can break this down, right? So I think one of my favorite analysis on how we can think about this challenge around physical AI is really using one of my favorite example on how we can make a pencil. Think about it. A pencil is something that's very simple or very straightforward. But even just a simple product like the pencil, it looks simple, but it has many components. It's a result of the forest, because we have the wood, right? The mines, the rubber, the metal, right? So it has many different components with it to build the pencil. And after you build out the pencil, you still need to shape it. You still need to deploy it. You still need to build that into the global supply chain so that you can buy a pencil today. So something that as simple as a pencil can be as complicated as a network that involves in many different layers. You have the wood, the graphite, the rubber, the metal, the machines, right, and the shaping. So a simple thing like the pencil is already a complicated network, and it's a system, right? And now think about physical AI. Physical AI is so much more complicated than a pencil, but it has the same problem. It has too many layers, and many layers introducing many layers of complexity here as well, right? So for physical AI, we have the software, the hardware, manufacturing. We need to think about the safety side of the issue. We need to worry about how do we deploy different physical AI applications. And we need to think about out of all these applications, right? What kind of verticals, different vertical application. And if we run like a quick breakdown on different layers of physical AI, right? So software is about perception, planning, and policies, right? So, how do you capture the environment? How do you do the planning on the execution, break down a comprehensive task into executable steps? How do you run different simulations? How do you do the evaluation? And also for the controllers, how do you handle all the user interfaces as well, right? And then we have, of course, physical AI. We are talking about a lot of things on the hardware side, right? And hardware involve so many other things, right? Sensors, motors, chips, manufacturing, and then we need to think about the power, the cost, the latency side of the things, the robustness, right? Whether this is something durable to use or not, and also where do you handle the manufacturing and the supply chain side of the things. Supply chain is another beast on its own, right? So even a brilliant system cannot just scale if the parts, the manufacturing, the integration, and the logistics, if all these things cannot scale with the product essentially cannot scale. So manufacturing is always a huge problem to solve, and that's why for the past few years we see that in the tech industry it's a great trend for the U.S. to bring the manufacturers back to the U.S. as well. The other thing is deployment. Deployment wasn't quite an issue in the software side of the world, because back in the days we have this kind of like CDs and different hardware medium to do the deployment. Nowadays with the internet, we just simply click a button and the software is downloaded, right? No longer it's a solved problems for software, but for hardware, deployment is still a very, very urgent issue, right? It happens in very specific places for specific use cases. Each location is unique. It has its own unique workflow. It has different safety requirement. It involves different operators, constraints, and different paths for adoptions as well. And also, different vertical brings in different challenges. So it's one thing when you mention, hey, I have this, for example, this robot, but when you are taking the robot into a safety inspection type of application, it's very, very different versus when you take the robot to, let's say, a simulation or data collection or warehousing automation type of scenarios, right? So when we are looking to the space, we also need to think about the vertical applications as well. But here's the thing, right? Because it's such a complicated system that involve so many different layers, there are global ecosystems created to solve all this kind of to solve all these problems and to decode a complicated problem into simple and executable and solvable little problems, right? It takes an entire global ecosystem to break down this complicated challenge that, for now, as I mentioned earlier, the software side of the intelligence is partially solved, but for physical AI, we are just at the very beginning. So for the past few years, me and Michael, we've been traveling all over the world, connecting with different regional ecosystems all over the world to understand and to collaborate with different ecosystem creators, ecosystem builders, and different players and counterparts in all these regions, right? And I think the simple takeaway, if we can do like a regional breakdown, right? So the entire ecosystem is global, but different regions have different strengths. For North America, obviously the frontier research, North America lead the frontier research. The best labs and the best researchers are here, right? And also, the cloud infrastructure is aggregated here, and most importantly, the capital, right? We here in the U.S. can attract capital from worldwide. So North America is a leader in terms of research, cloud, and capital. Asia, obviously, Asia is a leader in terms of manufacturing, supply chain, and robotics manufacturing as well. Europe, automation has, for such a long time, European has been the leader in terms of manufacturing, and especially precise and advanced manufacturing. And European countries in general, they employ a very strict policies around safety and making standard as well. Other than Asia, North America, and Europe, there are a number of emerging hubs such as Middle East, Southeast Asia, and Africa that specialize in very, very different things, from capital to infrastructure and a few test bed on a few experimental stuff, to some of the very front end of the supply chain, right, where minings and the raw materials are getting discovered and are getting collected as well. So the real challenge when we think about the global ecosystem for physical AI is how can we efficiently to coordinate all these different regions, all these different layers, and all these different ecosystems together so that they can seamlessly and organically work with each other, so that we as a human civilization can collectively solve these problems as soon as possible and make greater, faster developments in this space, right? So I think with that, our approach at Depth Map Ventures, we have identified a single layer that we think is consistent across many different ecosystems, and it almost can serve as an equalizer that can seamlessly integrate it with all different layers and with all different ecosystems. And here I'm gonna hand the phone to Michael, where he's gonna show you exactly what our plan is. So Michael.
Thank you, Ryan.
Yeah.
Thank you, everyone. So the opportunities coordination, what is this layer that's shared among everything? It's actually how Ryan and I got to know each other, because we both worked for the same lab at NYU, what was the Media Research Lab and became the Future Reality Lab. This is a lab that was doing physical AI before it was even called physical AI. We called it VR, we called it AR, we called it XR. It was using virtual world, simulating the physical world in a virtual world, using robots to try to give a glimpse of the future that we might have in 5 years. So luckily, Ryan and I, we spanned different eras in this lab. Ryan was there in 2009. I was there from 2016 to 2021, running commercialization for the lab. And so how does this translate to a single layer? Well, hardware supply chains are regional. Deployment environments are local, capital's uneven, but research is globally legible. Everybody publishes research. Everybody understands what a research paper looks like. And I'll show you some examples of what research papers look like if you're not familiar. But what does this mean for us? It means that small labs can enter the global conversation. They can publish their research and the whole world can disseminate it. We've already seen very big labs get a lot of funding. You have Yann LeCun, our former professor from NYU, left Meta, raised $1 billion right off the bat. You have Fei Li from Stanford, $1 billion. Mira from OpenAI with Thinking Machines raised hundreds of millions of dollars. But the future is in these small labs. How? Well, I'm gonna give you a baseball metaphor. Anybody here a baseball fan in the room? Okay, so imagine that you're trying out for the major leagues. Open source software is like the tryouts, right? What we're doing is essentially Moneyball for researchers. That's our play. So in the movie Moneyball, the book Moneyball, what they did is they realized in the early 2000s that people were overspending. Major league teams We're overspending on star players. Players like Johnny Damon that looked like a star. You'd think, oh, this guy's going to fill up the stadium, right? What he didn't do was he didn't buy wins. How did you get wins? How did a team buy wins? Well, you need to get hits, to get runs, to win the game. And they figured out statistically what players could get the hit when it mattered to get the run to win the game. So how do you do that for research? Well, basically what you have to do is you have to identify when research becomes infrastructure. And so what do I mean by that? I mean that, like, the ecosystem, it doesn't mature. It doesn't appear first as a mature market. It appears as paper. These papers are associated, many of them nowadays, with code. And the code is maintained by developers who have published the research. Now there are, in this physical AI space, there are 15 new papers every single day that have code associated with them. If you've ever read a research paper, I mean really read it, looked at all the code, identified what's going on, not even tried to implement it, it takes over an hour to do. So nobody, just like no one person can make a pencil, nobody can read 15 papers a day. So, what do we do at DepthMap? Well, we've made a graph for the entire ecosystem where we track all of these papers. We use language models to do this, of course, and we can identify, just like a depth map can do, what is near and what is far. Everybody in this room is in the VR space. We've worked with depth maps before. They represent a 3D world in 2D images. What's close to you is white, what's farther away from you shades to black. So we like to think that we're doing that and making things clear in the research paper world. So what do I mean by that? This is your typical research paper. You get a PDF with an abstract, and it tells you all about the claims that the papers make. How is this paper contributing to the science? What we do for these papers, for our signal, is we look at the implementation signal of the paper. So that same paper, we translate it into a database that we can then display on the web. And of course, we can look at all this data with our language models. So here you see the same paper, and you can open up the paper at the original URLs. You get a dashboard for it. And then what it does is it links it to the actual GitHub repo on the same page. And we can look at the entire stack of the paper. What did they use? What libraries, what models did they use to actually build out this paper? How much activity does it have? And what claims does a paper make? And as we scroll down more on the page, we'll see exactly what code translates to the claims that the paper makes. So what this paper is saying is that Star VLA provides a modular backbone action head architecture for VLA research. VLA is Vision Language Action Models. This is what helps a robot navigate the world. So how does it do it? Well, here's the exact code that maps to that claim. And you can drill in on GitHub and evaluate that code yourself to see if you agree with it or not. Then eventually we're going to have community support where you can upvote or downvote the claim and see if it's really being addressed in code. But this is the first website of its kind that does this, and we're using deeper analysis of these signals for our fund to back the researchers. So when a paper becomes code, evidence changes, and the ecosystem can inspect, reuse, fork, benchmark, and build on it. So we want to make that way easier for researchers. We want to make it easier for investors, and we want to make it easier for people that are implementing research papers and the software behind them as infrastructure in their businesses. So, as I said, stacks reveal the infrastructure underneath. So all the dependencies and toolings, they reveal what physical AI teams repeatedly need. These repeated needs become the infrastructure opportunities. Also, one of the things that we try to do is as investors is identify the bottlenecks that are repeating themselves, right? Like when we're thinking about markets, before the market's obvious, you can usually see the same pain points repeat themselves over and over and over again. So in these research papers, as people are trying to solve the same problem in different ways, we can track that. We track it week by week to see how much activity the GitHub repo is getting, how many contributors they have, how many people are forking it into their own projects. So essentially, we're mapping the signals before they become markets. This is our thesis in one sentence. We're watching the research turn into infrastructure in real time, and we're revisiting these things every week to update so we can see how the trends are ebbing and flowing. So what do I mean by that? Well, we actually put together this trending database list. So you can see, you can go to the website right now if you go to depthmap.com, and you can see trending research this week, this month, and this year. And every single day, we're adding 15 new research papers to it. Every single week, we're revisiting all the GitHub repos and tracking what's changing. So this is live right now. These are all the top papers this week. And if you're implementing cutting edge research into your physical AI applications, and we're happy to answer questions, I think we'll have some time after this, we can talk about like where you can get this data and how you can build on this. So the idea is that when research becomes reusable infrastructure, that's when everybody wins, right? That's when the researchers win, they build startups. That's when the industry wins, they get access to open source software. That's when the open source software becomes the enterprise default. So one of our big themes that we're looking at in physical AI is that the better synthetic data that you have, the more that you can test the physical world in the virtual world, the better you'll be able to train robots to be able to work in the physical world. So all of this we see as a cycle that repeats. And with that, I'm going to hand it back to Ryan to close us out. And we'd love to chat with all of you more about physical AI and how the emerging world is forming.
Thank you, Michael, for the amazing walkthrough. You see, I think back to our original topic here, what we are doing is essentially identifying the signals and also find a unified and a layer that seamlessly connect with global ecosystem in the physical AI space. And that unified layer is really research and open source, right? But not only are we looking into the research and open source world, but also we are building a tool to identify what's a trend, what's a signals, right? How can we use this kind of intelligence when we are making our decisions in the future? So it's pattern recognition, but pattern recognition is giving us great insights on what the future can look like. So essentially what we are doing, we make emerging directions visible. We connect papers, code, people, and stacks together, right, by providing these kind of functionalities. And also we support the builders behind the infrastructure. We help different regions to collaborate, because no matter which region you are coming from, you can be a researcher, and it doesn't matter where you are come from and where you are based. Make no difference on what you are researching on. we help researchers publish and make their code open source. And we help builders to turn the bottleneck into tools. And for the investors out there, we support the infrastructures before it become obvious, right? So even before the researchers are thinking about entrepreneurship, before they even realize that, hey, this is a great opportunity to build a company based on our research findings, we can identify these signals and we can work alongside the researchers to turn their research into business as well. And also, to a lot of regional partners around the world, we help to create real-world testbed through what we are doing here. So we're really tracking, supporting, partnering, buildings, and investing through our activities at DevMath Ventures. And we believe that physical AI will be built by ecosystems. And our approach is making the ecosystem much more visible by providing all these signals as well. So if you've ever heard about this term Neo Labs, that's what Michael mentioned previously about word labs, thinking machines, AMIs, right? All these billion-dollar companies started by a group of researchers. But before they started companies, most of them are researchers at small labs. They don't have that level of visibility. They don't have, hundreds of millions of dollars in their bank. They started with a research idea, right? We want to identify all these researchers when they are still working at small labs, when they are still, iterating their ideas, and we want to capture the early signals and work in the very, very beginning with the researchers to make the ecosystem visible. So thank you for joining us on this session. This is our LinkedIn. Please connect with us. And also, I think we have 2 minutes left. So if you have any questions,
all right, let's give a round of applause for Ryan and Michael. All right, any questions? Okay.
Yeah, we have
We'll start off with you.
Hey guys, love what you're building here. I love looking at the trends at a macro level. Curious if it would be helpful, or if you have built in already, the data at which people connect, say on social platforms, to further predict really where the trends are going as it relates to research, as it relates to funding, as it relates to big partnerships.
Michael.
So if people can connect with each other, if they share the same interests, is that what you're asking?
I'm asking if you had that data.
Yeah.
So if you had like data of connection with like say a VC and a founder,
Yeah.
or a couple labs, or whatever the people are, whatever sort of parameters you put out, if that data would be helpful to what you're trying to accomplish.
Yeah, absolutely. So what we are going to enable is the researchers that have published their code on GitHub, we're going to allow them to sign into the website with their GitHub. And so anyone will be able to sign in and express interest in the research.
Okay. I have LinkedIn connections and the date of. So if you guys want to chat, right now it's only H&I's, VCs, and family offices,
Yep.
but we're expanding.
Love it.
Yeah.
Yeah, let's definitely chat more.
Thank you for sharing your insight about the ecosystem and physical AI. And my question is, currently, it still seems like there is a long way to go for physical AI. And what is the biggest hurdle you think of in the ecosystem of the physical AI, and how can you solve it?
Great question. I'm going to answer it, and Michael, feel free to chime in. There is a short-term and a long-term challenge, right? So, short-term, mid-term, and long-term. So, very short-term, I think is really, there are so many layers, and different layer introducing different complexity, right? So, software, hardware, manufacturing, supply chain, how can you integrate everything together organically, deployment, right? So, they are the short-term, most immediate term. In the mid-range term, in the next 3 to 5 years time horizon, I think the key bottleneck will be will be data and also the intelligence, right? Currently, VLA, VLM, as Michael mentioned, visual language action, it requires a lot of high quality data. And synthetic simulation data is one way to generate them, but it's not a very high quality in general. So currently the state of the art for high quality side of training data for VLA, VLM are still through a teleoperation. And teleoperation means you are manually doing teleoperation wearing some kind of motion controllers, right? So it's a very, very human labor intensive type of work. And that's where the big promise of world model, right? How can we build a model that's kind of beyond the large language model type of architecture that can understand the world more natively? This is behind the big promise of the world model. So if we can make any kind of breakthrough on the model side, I think that will advance the intelligence layer for robotics in a great way, right? So that's in the midterm. Long term, I think it's also like a global ecosystem type of issue, right? So not only connecting software with hardware, integrate everything, but also think about geopolitical, right? Think about consumer adoption, think about the ethical side of the things, right? That's some of the long-term challenges as well.
So yeah, everything Ryan said, and I'll give you guys an illustrative example. So I want you to close your eyes and think of an apple. Like think of an apple and imagine you reaching up and grabbing that apple, like in 3D space, right? How many of you thought of the word apple there? And saw the APPLE spelled out in your mind? Probably nobody, right? But a robot right now with these vision language action models, they're actually thinking in words before they can visualize those words into the 3D world. And where it needs to go, where it needs to get to, and a lot of these labs are working on it right now, is on the software side. They need to be able to predict the next state and move from state to state visually and physically in the world before they think about, oh, I need to go over here, and then I need to move my legs, and then I need to move my body, and then I need to, nobody thinks like that. We just know what we have to do. We've learned to crawl before we learned how to talk. The robots have learned to talk before they learned to crawl. And that's the big problem. So once that's solved, they'll be a lot faster, and things will be a lot more interesting. And that's probably going to happen within the next year or so. And then there'll be a new hurdle to get over, right? And that's what we're going to be working on identifying, and the researchers will get there first, and hopefully we can back them, and you guys will all benefit from it.
All right, let's give a big round of applause for Ryan and Michael.